So maybe while others are getting in the class, no, let's move on and have this lecture. So maybe if we'll finish this early on, then we can proceed with what I assigned you, no, earlier. No? So what is basically, this chapter on chapter this is chapter 6, no? So electromagnetic induction will require us, no, the presence of a magnet, no, or magnetic field for that matter, and the magnetic field will be it will come in contact with a wire, a conductor, no, a metal wire, and these two allows the generation of current, no. So current therefore can be created, no, if we have, no, a magnetic field and a moving wire, no. Now we've seen that now when we perform our we've seen that now when we perform our activity on Faraday.
Nabasa.
So we have Faraday's law, and in our Faraday's law, if you recall, no, in using our FET simulator, we have, no, a coil of wire, and that number of coil actually, no, affects also, no, the amount of brightness in the bulb. No? Now, other than the brightness of the bulb, no, we also measure it in terms of some voltage. No? Now, in this presentation, we call the voltage created in the wire there, no, as the EMF. No? EMF is short for the electromotive force. So, so EMF is measured in voltage, and that is what is created whenever we move the magnet, no, within a wire, no, or within a coil of wire. No? Now again, no, things that we notice there, no, how it affects the voltage that is developed, or the brightness of the bulb, is when we move it now with some rate. No? So how fast we move the wire, or we move the magnet, no, affects the brightness. No? So the more, if you want the bulb there to light a little bit more brighter, then we need to move the magnet faster. No? So actually, the movement of the changing of the poles of the magnet is the one that affects the activity. No? So again, you can check that now by going into the FET simulator, where that is referring to the Faraday's law. So again, another definition of magnetic induction or electromagnetic induction is the production of the EMF. EMF is short for the electromotive force across, no, a wire or an electrical conductor. No? And the magnetic field has to be changing, no, of course, when we keep the poles there, no, change from south to north, no, south north, south north. We notice that the voltmeter there, if you connect it to your bulb, will register, no, a higher voltage value. No? Now here are the two individuals that do those activities. No? So we have Hans Christian Ørsted, and the other guy is your Michael Faraday. No? So we perform his experiment. No? And here's a picture of the activity of Faraday, no? Michael Faraday. So he kind of pushed the wire, no? into, no? into or he pushed the magnet into a coil of wire. No? And whenever he moved it back and forth, no, we notice that the voltmeter there, no, reads some value. No? So there's our voltmeter reading or an ammeter reading, no, that now swings the needle of the ammeter. No? Now, for those activities that will register, no, a very, very slight or a very, very small amount of current, they use another device called a galvanometer. No? A galvanometer is nothing more than a device with a meter here that records also, no, very small amounts of current. No? Again, no, this is the activity done by uh, Michael Faraday. No? So moving the magnet, no, back and forth, na, in a given coil of wire, and therefore, no, causing the fluctuation, no, of the current, no, from it swings right and left na ang needle. So it means that this is a changing current. No? So from positive, it becomes negative, no? And so on and so forth. No? Now, this is the beginning of what we call as alternating current also. So to produce alternating current, then maybe you'll need to move magnet within a wire. No? Now, characteristics of electromagnetic induction. No? For movements between bar magnet and conductor, there would be deflections, no? In the galvanometer. So the galvanometer or ammeter will swing from right, left, ang iyang needle. No? So it's a changing current. No? So current that they call that, no, as is alternating. No? Alternating current. No? Now in the bar magnet, no, if the bar magnet and the conductor remain steady, so if you keep the magnet just within the coil, no, they notice that nothing happens to nothing happens in the coil of wire. No? If the pole of the bar magnet is changed, no, so if you change it from north south, then the direction of the induced current changes also. No, so it becomes positive and negative as we keep on changing the pole. No, but if you keep the magnet inside steady, then nothing happens. No? Now, when the loops in the coil increases, now the deflection becomes greater. No? So there would be greater current or greater voltage that is generated whenever we add more number of turns in the coil of wire. No? So the number of turns affect, no, the amount of current, no, that is created, or the EMF, no, that is developed. No? Now here's the activity of Faraday. He made a coil of wire, of course. No? And in that coil of wire, he attached a meter, no, an ammeter or a galvanometer. No? Then he has to have a magnet that is plunged into, no, we can probably call it as plunging into the coil. No? So he made the bar magnet go, no, or move within the coil. No? So it has to move, no, with some degree of rate, no, or how fast or how slow it is moving. No? Now another way to do that is by letting a coil of wire here. No? Uh, we call it as a solenoid, and then we can probably pair these two coils, no, one which is attached to a battery and then one which is attached to an ammeter, no? And we'll notice that the one with the current, no, that is provided by the battery, no, will influence the other coil of wire. No? So when these two coils of wire are brought together, you'll notice that the ammeter here, no, will start to move despite the fact that the left coil does not have any battery. No? So a current will be developed in the next coil despite the fact that we only place the battery on coil number 1 or the coil on the right side. No? So when you turn the switch here on, then the other coil, no, which does not have a battery, despite that they are not attached, no, they are separated by some distance there, that the magnetic field, no, created in the first coil on the right will influence the production of voltage or current on the other coil. No? Now again, no, this one is an illustration of a diagram of a transformer. No? A transformer is one device that allows us to step or increase the voltage or to step it down, or we call it as a step down transformer. No? So we can increase the voltage or we can lower down the voltage. No? So I think they call this as what? Mutual induction, I guess. No? So the number of lines, no, or the magnetic lines of force that are developed, we can think of it as a magnetic flux. No? So in one surface of a pole, no, you'll see that there would be a number of lines of force that comes out, no, if it's a north pole, and there are a number of lines, magnetic lines of force that will get into that surface if it's a south pole. No? So but the amount of, or the density, no, of the uh, magnetic lines there, no, depends on what they call the magnetic flux. No? So probably, more lines means greater amount of uh, magnetic force there. No? Now, what are the laws of electromagnetic induction? So Faraday's laws, it states that the EMF induced in a wire is proportional to the rate of the flux through the loop. No? So how much or how fast is the magnetic field, no, going into, no, a given wire, or yes, wire, no, then the magnitude of the EMF will also depend on that. No? So meaning the faster the magnetic flux, no, then maybe, no, you will have a greater voltage, and lesser rate, no, of magnetic field, no, going into a given coil will have lesser, no, EMF. For Newman's law, no, the magnitude of the induced EMF is proportional to the rate of change of the magnetic flux linking the two circuits. And for Lenz's law, no, the induced EMF acts, no, to circulate, no, a current in the direction that oppose the change in the flux. No? So actually, no, if you have two sets of wires, guys, no, or two sets of coils, then there would be what they call as a counter EMF. No? So I think, no, in some generators, there is this thing that they call as a counter EMF that makes the generator, no, spin. So the spinning of the generator will be kind of slower, or more, it will need no more effort there, not to spin it, no, when the counter EMF becomes very large, no. Okay, so for our Lenz law, no, according to Lenz law, the direction of the induced current in a coil, no, is such that it is always, no, that it always opposes the one that cause, no, or produce it, no. So there's this slowing down probably, no, of the motion of the coil there, no? So there will be a kind of difficulty, no, in 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 the motion of of the magnet there, no? Now here's a picture of our self-induction. So usually, now this solenoid can also be called as an inductor. There's this thing that they call as an inductor. Now when we put a battery, guys, now in this inductor or in this solenoid, you'll see that um, if you'll connect an ammeter, no, across here, no? So let's say we'll put an ammeter or a bulb. Now you'll notice that once there is a battery here, no, then the magnetic field is then set up in the coil. No? But if you'll connect a bulb probably, no, across this solenoid, and after connecting the bulb, no, so of course the bulb will probably light up. No? You'll notice that when you detach the battery, no, even though there's no more battery and the bulb is lighting up, no, you'll notice that the bulb will not switch off immediately. No? So what you will notice, however, is that the bulb there, the brightness of the bulb, no, will probably, no, flicker, and it will die, no, but in a rather slow or in a paced manner. No? So it will not immediately, no, turn off its light when you remove the battery, no, especially if you have this solenoid, no, attached to the bulb. No? So the work of the solenoid there is to slow down, no, the flow of the current, but it will not cut the current immediately. No? So those are functions of solenoids or inductors, no, will prevent, no, the sudden change in the current. No? So if you will remove the battery and immediately, no, cut the source of the current, and the inductor will prevent it from suddenly, no, being cut. No? So the inductor or the solenoid will remove the current, no, little by little, no? Because this magnetic field will prevent, no, the immediate, no, removal of the current. No? So the magnetic field will maintain the current and will dissipate the current, no, little by little. No? So hindi ni siya gulpi, madula, or ma-off dayon ang bulb. No? If you have a bulb there, no, to check the presence of the current. No? So that's what we have for self-induction. No? So the current here now will be now will be dissipated, no, but rather, no, in a very slow manner, no. So amat-amat na siya madula, hindi na siya magulpi mautod, maskin dulaon mo na ang battery, no. Now in some welding devices, in some transformers, no, they have this mutual induction. So you have a pair of coil of wire, one with the source, no, or a battery, and then the other one, no, with an ammeter, no, so, or a galvanometer, no. So you'll notice that in this other right, or in the right side here, no, you will see a voltage or a current reading, no, despite the fact that there's no source of battery on this side. So again, the source of the current for this one is, of course, now the induction created by the left coil. No? So the left coil with a source there that is changing allows the production of the magnetic field. No? So other applications of electromagnetic induction. So we have motors, no, generators, transformers. No? So these are the very basic ones. No? And I think the other devices here are simply, no, an improvement of the previous one. No? Now, when we transmit, no, current, no, over long distances, no, so from the source, no, let's say a power plant, no, they use transformers, no, to step up the voltage so high so that, no, you can transmit the current, no, for long distances, no. So that's the function of transformers, no. When generators create the current, the transformers are the one, no, that are responsible, no, in transmitting them over great distances, no. So for very long distances, then they have to step up the voltage in several thousands of volts. Now, here are some images of transformers. You have some primary coil, no? So maybe the one on the left side is called as the primary coil, and the other side, no, is called as the secondary coil. No? So if the voltage on the left side, no, is kind of high, no, let's say this is 1,000 volts, no. How do you use the voltage that is 1,000 volts in your home? Then there is a transformer that will lower it down, no, to several hundreds of volts only. No? So the one that we see in our electrical post, no, maybe that's some values in thousands or 440 volts. 440 volts cannot be used inside our home because in our home we only use 220 volts. No, so you'll notice that there's that seemingly like a cylindrical object, no, in the post, no, that steps down the voltage there. No? So we call that as a transformer. And the voltage now becomes useful in our homes by stepping it down, no, to 220 volts. No? Now here's a picture of a generator. So there's a coil of wire that is run through, no, a magnet. And because of that, now you are able to produce now a current now that is flowing in this coil of wire that is continuously spinning. No? So the coil is the one that is spinning. No? Now the one that makes it spin is this shaft, no? Or this rotor, while these magnets are held steady. No? Maybe you have a U-shaped magnet there that allows you to make, no, two different, no, poles, no, meet each other. No? So when this coil cuts the magnetic field, then you'll see that the bulb or the voltmeter there will register a current or a voltage. No? Okay, so this is our uses of our magnetic induction. So hopefully, no, you understand that